Hi everyone. This is going to be a video on basic trigonometric equations for pre-calculus. I'll tell you that this is going to be a little different from the most recent lessons we've been doing because recently we've been learning about trig identities. We've been proving trig identities, we've been using them for things, but this lesson and the next one are going to cover solving trig equations, which is a little bit different, and it's not really going to use much in the way of trig identities, but it still kind of goes in this chapter as part of analytic trig. So let's go ahead and get started. All right, so there are going to be two videos, two lessons on this topic. So this first one is called Basic Trigonometric Equations, and then in the following lesson we'll have some other trigonometric equations. Let's start by saying trig identities, which we've been talking about lately. Trig identities are true for every value of the variable as long as both sides are defined. For example, a good trig identity is sine squared of theta plus cosine squared of theta equals 1. Now, I know we've written that trig identity a bunch of times, and we've written it with a different variable each time, probably. We've seen this trig identity where the variable was called t, we've seen this where the variable was called x, and we've seen it where the variable is called theta. And it's all the same thing, it's just different labeling. Usually when we call something theta, it's because we're thinking of it as an angle, but it's still just a letter. I mean, theta is still a letter, it's just a Greek letter. All right, anyway, so you could put in any value of theta you want. You could put in 7 radians, and this is true. You could put in 123 degrees, and this is still true. You could put in 1,000,000. This is still true. All right. Now, we'll look at equations that are only true for some values of the variable. And I'm using the word equations here, and I'm not using the word identity. It's no longer going to be considered a trig identity. It's just going to be an equation, because an identity has to be true for every variable, for every value of the variable. But if it's only true for some values, we could still call it an equation. And above, I used the variable theta because theta is usually what the variable is going to be called in this lesson. So we're going to start with what are called basic trigonometric equations. I mean, that's the title of this section. And they are going to be of the form t of theta equals c, where t is a trig function and c is a constant. And I'll show you what we're going to be doing. Usually in math when we have equations, usually we want to solve for the unknown variable. And that's what we're going to be doing here. We'll have something like sine of theta equals a constant, or cosine of theta equals a constant, or cosecant theta equals a constant. And all of those would be basic trig equations, and we want to know how to solve for the variable theta. So I'll show you an example. Let's solve the equation cosine of theta equals the constant square root of 2 over 2. We'll talk through this together. We've seen things like this before. I don't know if we've ever phrased it this way. Solve the equation. But yeah, there's a variable. We want to solve for it. We want to find out what theta is. We could think about the unit circle. We can go back to that. We could say, like, do we know a place on the unit circle where cosine is equal to this number? Yeah. Yeah, cosine is the x-coordinate of a terminal point. So you could say, oh yeah, this place right here, right? So we could say that one solution is theta equals, let's write this in radians, okay? Pi over 4. But that's not the only solution. What about down here? What about this angle? What if you went around the unit circle from our usual starting position and you stopped here at this terminal point? How far around have you gone in radians? It's 7 pi over 4. If we're going in the positive direction, then that's 7 pi over 4. So it seems like both of those should be considered valid solutions to this equation, because a solution to an equation is just a value of the variable that makes it true. So yeah, cosine of pi over 4 equals this, cosine of 7 pi over 4 equals this. So it looks like we found two solutions. However, there are also other solutions, aren't there? Well, I don't see anywhere else on the unit circle that's going to make this true. But there's still other solutions. How about, from this one? Instead of just going pi over 4 around the unit circle, what if I went pi over 4 plus another lap around the unit circle and stopped here? So pi over 4 plus 2 pi. That gets me to the same terminal point, right? Coterminal. These are coterminal angles. So if you put in this number for theta, the equation is true. Cosine of this does equal the square root of 2 over 2. Couldn't you do the same thing with this one? 7 pi over 4, but say, like, let's go another 2 pi around. Let's do an extra lap. Maybe it seems like it's a, you know, it doesn't seem as simple as the original solution, but it's still a solution. What about if we went around the unit circle an extra 2 times? So we're adding 4 pi. Are these, let me ask you this, are these different solutions? Like, am I actually describing different solutions? Because they're coterminal, right? So would you just say that they're the same angle? Well, no, they're not equal to each other. As numbers, these are different numbers. So they are different solutions. So we've actually written out 6 different numbers, 6 different solutions to this equation. And now you're starting to get the sense that it's not just these 6, is it? It's going to be infinitely many, because we could add 6 pi, we could add 8 pi. Or what if we subtracted 2 pi? What if we decided to, like, go in reverse? Or if we subtracted 4 pi, that would also work. Or 6 pi, or seems like any even number in front of pi. Like, what if I subtracted 112 pi? We would, I guess, go backwards around the unit circle a bunch of times, and then we would go plus pi over 4 to get to the correct place. So how do we write all of the solutions when there's so many of them? I do feel like the solutions are kind of divided into these two groups. There's like this family of solutions, and this family of solutions, the ones that are based on pi over 4 and the ones that are based on 7 pi over 4. So let's get to the point. How do we write, I don't want to write also, I want to write all solutions. How do we write them? We need a way that somehow describes these two families of solutions and explains that we can add any multiple of 2 pi, any integer multiple of 2 pi, like 2 pi, 4 pi, 6 pi, 8 pi. So what we write is theta equals pi over 4 plus, I want to say any integer multiple of 2 pi. And the way that we do that is we say 2k pi. We also say this one plus 2k pi. And we say this is happening where k is any integer. And that describes all solutions to this equation. If cosine of theta equals square root of 2 over 2, theta has to be a number of this form. It's either going to be pi over 4 plus 2 times an integer times pi, or it's going to be 7 pi over 4 plus 2 times an integer times pi. So there's infinitely many solutions. But let me be clear about something. There's infinitely many solutions, but that doesn't mean every angle is a solution, right? Because take pi over 3, that's not a solution. So you could have infinitely many solutions, but they fit into this form. Anything of this form is a solution. I want to show you visually, what does this look like? All right, visually. When solving, because I just moved it off the page, so I'll write it again. When solving cosine of theta equals square root of 2 over 2. Off to the side, I'm just going to say note, square root of 2 over 2 is approximately, well, I know that the square root of 2 is around 1.4. So if I divide it in half, then it should be around 0.7. It's actually around 0.707. All right, so I wrote a few extra digits there. When solving this, where does cosine of theta equal 0.707? Now, we already have tried to visualize this on the unit circle, but there's another way that we can visualize it, isn't there? We could look at the graph of cosine. Maybe we haven't graphed cosine in a while. Remember that the highest up that it goes is 1, the lowest it goes is -1. You know, some important points might be pi and 2 pi. Let's draw 3 pi. Here's negative pi. And I'll put little marks at like pi over 2, 3 pi over 2, and so on. All right, so what does the graph of cosine look like? Passes through a y-intercept of 1. By the time it gets to 2 pi, it's back up there. So it looks something like this. Yeah. All right, I just drew as much as I could on my page. Let's go a little bit further in this direction. It's a periodic function, you know, it keeps going on and on forever. All right. I actually went as far as I could possibly go on my page to the left and right. Now, if that's a graph of cosine, I guess if I'm doing this, then maybe I have like a y-axis and a theta axis, because I guess the variable is theta, not x. Okay, so I labeled the axis theta. Where does cosine of theta equal 0.707? Well, we see the places where it equals 1. 0.707 would probably be about here. Can we say that it's about there? I'm going to draw kind of a horizontal line here. And just to be clear, I'm going to make this as a dashed line, but it's not an asymptote. Sometimes in math, we draw dashed lines as like a sort of guide. It doesn't always mean that it's an asymptote. I just want to see like the height, 0.7 is about here. Okay. It keeps going. I'll draw arrows on it. All right, so where does cosine equal that? It happens in a bunch of places, doesn't it? It happens here. That's one place where it happens. Hey, guess what? Guess where that's happening? Look at this. That point, if I drew this correctly to scale, that point is exactly at pi over 4. That was one of the answers that we found. Where's the next place where it happens? It happens here, which, again, if I drew this perfectly to scale, that would be happening at 7 pi over 4. So those were two of the answers we found. We found this answer here. So what's this answer? This answer is pi over 4 plus 2 pi. Takes you to here. And then there's this answer. This one is 7 pi over 4 plus 2 pi. Gets you to here. And then you can see that there's going to be another point that's like going off the edge of my page. There's going to be another solution here. I guess that solution all the way at the right, that's kind of if you took pi over 4 and added 4 pi, because I add 2 pi, and then I add another 2 pi. Gets me to here. So you see how you can visualize this based on the unit circle or based on the graph. Now, this is probably the only picture that I'm going to draw today, because we could, or I should say, this is the only graph of a trig function I'm going to draw today. We might draw some unit circles for scratch work, but I just wanted to show you that it makes sense that equations like this have infinitely many solutions, because it's all the places where the curve is at a height of 0.707. So let's do another problem. Okay, I don't know why, but my recording just stopped, so we're gonna do this again. Where we just left off was we were about to start a new problem. So suddenly I shifted the piece of paper here because I had a recording problem. We were about to start a new problem. So let's solve for theta in the equation. Sine of theta equals 0. This is another basic trig equation, right? It fits the definition, or it fits the basic form that we talked about earlier. So let's talk through this. We could use the unit circle. I don't think I'm going to draw a graph of sine this time, but I will draw a unit circle and say, do we know anywhere on the unit circle where sine of theta equals 0? Well, yeah, sine of theta is supposed to be the y-coordinate of a terminal point. So I know two places on the unit circle where this happens. These two places. And I'm going to say that this one, we stick with radians in this section. Okay, so we know that sine of 0 radians equals 0. So that means theta equals 0 is a solution. We know it's not the only one, but it is a solution. What about this other one? Let's try to point to it. This is sine of pi equals 0 if we're sticking with radians. So theta equals pi is a solution. I left myself some extra room with each of these because, of course, we could add a multiple of 2 pi. You know, we could say also theta equals 2 pi, 4 pi, 6 pi, etc. That's me taking 0 and adding 2 pi to it, or adding 2 pi twice, or adding 2 pi 3 times. And over here, what happens if you add 2 pi to this? You get 3 pi. Or if you add it again, you get 5 pi, 7 pi, etc. You could also go in the negative direction. I tend to be writing the positive ones, but you could have negative 2 pi is a solution to this, right? What would negative 2 pi look like? You'd go from the starting position and you'd go in the negative direction, a distance of 2 pi. That would also get you to a place where sine of that equals 0. So let's try to write all solutions. So it seems like we have 2 families of solutions. We could say theta equals, should we say 0 plus 2k pi? It seems a little silly to write 0 plus, because 0 plus doesn't really do anything. But we'll write it. We'll write it anyway. 0 plus 2k pi, and theta equals pi plus 2k pi. We should say where k is any integer. Now, I'm not going to put a box around this yet. Hold on a sec. Did we describe all of the solutions? Yes, we did. But I think there's a nicer way that we could write this. There is a simplified way that we can write this set of all solutions. Do you see what it is? Well, let's look up here again. What's like, if we were to list out all the solutions, what would they be? They'd be 0. Let's try to list them in order. 0, pi, 2 pi, 3 pi, 4 pi, 5 pi, 6 pi, 7 pi, 8 pi, 9 pi. It seems like we should just say any integer multiple of pi. And we can do that by just saying k pi, where k is any integer. So sometimes you can do this sort of thing where you write the answer in a simpler way because the 2 families of solutions were able to be just merged into one. But instead of 2k pi, it's now just any multiple of pi. All right, and I think that that is a simpler way of writing the solution. One thing that I want to say at this point is we just did 2 problems, and we're going to do some more. But you notice that in both problems, we had to say where k is any integer. And what's going to wind up happening, I think every problem in this section, the answer is going to be theta equals something where k is any integer. Where k is any integer, where k is any integer, and we're going to keep writing that over and over. And you might get tired of writing that, and you might say, like, is there some shorter way that we could do this? And the answer is, you could just skip writing this phrase. You could, I'm putting it in parentheses right now. It's okay if you skip it and you just say the solutions are theta equals k pi. Because when we're solving trigonometric equations and we write the letter k, it's sort of implied that we mean k is any integer. It's sort of clear from the context of the problem that we're working on. So if you want to skip writing those words, that's fine with me. I'll tell you that personally, my own preference is I think we should write this every single time. But the reason that I'm making it optional to write it is because the textbook that I'm following along with, the recommended textbook, they sometimes don't write this. And if the textbook doesn't write it, then I feel like I can't really make you write it. So, to be fair, we'll say it's optional, that phrase. But use the letter K. Don't use a different constant. All right. What else have we got? So we did 2 problems so far, and they were both in what we were calling this basic form. A trig function of theta equals a constant. And now we need to talk about other trig equations, like what if it's not in this nice form? What if it's not just trig function of theta equals constant? Well, there's going to be a few different answers to that. It really depends on what the equation looks like. But one thing that we could do is we could try to rearrange other equations into that basic form. Remember, capital T just is like any trig function. In one problem, it was sine. In one problem, it was cosine. It could be any of the 6. So I'll show you an example. You know, it makes sense. If we have something that's in a more complicated form, let's try to convert it to the basic form. So let's say we want to solve 2 sine of theta minus 1 equals 0. This is not in that basic form. It's not just it's not like sine of theta equals a constant. How about this? I'll start this one, and then once we get far enough, I'll ask you to finish it. What do you think? What do you think? Add 1 to both sides? Oh, my pens are dying. Add 1 to both sides. Let me see if I have a better pen. All right, so we're adding 1 to both sides, and that gets us to 2 sine of theta equals 1. And then let's, we're trying to get it into this basic form. We want it to just be sine of theta equals something. So let's divide both sides by 2. Think of it that way, or you could say we're multiplying both sides by 1/2. Either way, we get sine of theta equals 1/2, and now it is in this nice basic form that we like. Because it's a trig function of theta equals a constant. So we did it. We rearranged into the basic form, and now we can try to solve it like we did with the previous 2 problems. So I'd like you to give this a try to finish it, and you can pause the video and then check back with me in a minute. So we are trying to solve sine of theta equals 1/2, which is actually equivalent to this original problem. I'll draw a little scratchwork unit circle, and I'll say, where on the unit circle does sine of theta equal 1/2? I know 2 places where it happens. It happens here, and it happens here. And I'm thinking that those 2 solutions are pi over 6 and 5 pi over 6. So all solutions, let's just go right to it. All solutions. It's going to be these 2 families of solutions. You take either one of these and add multiples of 2 pi. So I'm going to say theta equals pi over 6 plus 2k pi. Remember, k can be any integer, which means k could be positive, it could be negative, it could be 0. Plus 2k pi, where k is any integer. And that's it. So all we had to do was a couple of extra steps before solving it, and it was really just kind of felt like algebra, adding 1 to both sides, dividing both sides by 2, just some stuff like that. I'm also going to say that for some problems, we might need other algebra steps. such as, what do you think is a popular algebra step? Factoring. Yeah, that's what we'll need for some problems. I mean, factoring wouldn't really help with the one we just did, but I'll show you a problem where factoring is going to help. So sometimes we can't actually get it into the basic form, and we need to do something else instead. And you have to kind of figure it out based on what the problem looks like. So let's say I want to solve cosine squared theta minus 3 cosine theta plus 2 equals 0. And I'll talk us through this one. I don't think we're going to be able to get this into basic form. I think the cosine squared is what's going to throw us off. All right, let's move some things. You might think, is there some trig identity we could use? Maybe like a formula for reducing powers to get rid of the cosine squared, and then we could like get it into the first power of cosine, see if that helps. That might be one way to do it, but I think we can do this without trig identities. So I'll show you what I have in mind. First of all, as a side note, I want to say that this problem kind of reminds me of something. This kind of problem, I'm going to say, looks like kind of looks like a polynomial. Do you think it looks like a polynomial? Does it kind of look like x squared minus 3x plus 2 equals 0? Do you see the similarity there? I mean, it's not a polynomial. It involves cosine. It's definitely not a polynomial. But I feel like it's kind of in this form where it's something squared minus 3 times that something plus 2 equals 0. So yeah, it's kind of in that form. And if you gave me a problem in this form and asked me to solve it, I would probably factor. I would probably factor and be like, oh yeah, this factors to x minus 1, x minus 2. And then I would continue from there and I would get some solutions, right? That's what we're going to do here. We're going to factor. So the stuff that we did off to the side as a side note, maybe you actually could just consider that scratch work, because that sort of shows us that this problem factors to cosine theta minus 1, cosine theta minus 2 equals 0. Pretty cool. From here, this leads us to two directions. This means cosine of theta minus 1 equals 0, and this one means cosine of theta minus 2 equals 0. And we'll try to work with each one of these. This one, we could add 1 to both sides and get cosine of theta equals 1. And over here, we could add 2 to both sides and get cosine of theta equals 2. So it looks like these are in basic form. These are in basic trig form where we can have, trig function of theta equals a constant. And we've done, 3 problems already like that. So we could do 2 more. Which one of these do you want to do first? How about, let's look at this second one first. Cosine of theta equals 2. Do you know anywhere on the unit circle where cosine of theta equals 2? This never happens. This never happens. There's no value of theta that's going to make cosine of theta ever be greater than 1. You could think of that by thinking of the unit circle and say, when is there going to be a terminal point that has an x-coordinate of 2? That would not be on the unit circle. So this little part of the problem has no solutions. I'm going to tell you another way that you could think of it. Remember earlier we drew a graph of cosine for some other problem we were working on? When does this graph ever get to a height of 2? It doesn't happen. A height of 2 would be up here. So when does cosine theta equal 2? Never. So, okay. What about cosine of theta equals 1? Cosine of theta equals 1. All right, so this happens when theta equals 0, 2 pi, 4 pi, etc. So all solutions to this equation are going to be, we want to say multiples of 2 pi, so we'll say 2k pi for any integer k. All right, does this remind you of anything, by the way? We finished this problem, we're done. Reminds me of something. It reminds me of near the beginning of the semester, we had some problems when we were trying to solve exponential equations. And there were some things earlier that involved e to the x. This is like before we even talked about trigonometry. We had exponential equations, and I think I had one where I said a little side note, and I said, this problem kind of looks like a polynomial. If it was a polynomial, we could factor it, and then we factored it, and it was like e to the x minus 1, e to the x whatever. And yeah, it is kind of similar to that. I don't know if you remember that problem or not. So sometimes when something is not a polynomial, we can still use what we know about polynomials and factoring anyway. I have a problem that I think I'd like you to try, and I'm going to give you a hint. So let me write the problem and the hint. 2 sine theta cosine theta minus cosine theta equals 0. So this is not in basic form, and my hint is going to be factor out cosine theta. All right, so I'd like you to pause the video and try that. So if we factor out cosine theta, we get cosine theta 2 sine theta minus 1 equals 0. Wait a second. 2 sine theta minus 1. Didn't we do that problem earlier? Yeah, we did this actually. Well, this sends us on two different paths, though, so let's write both of them. This says cosine of theta equals 0, and this says 2 sine theta minus 1 equals 0. And we did this problem. We did this earlier. So what should we say here? I guess we got, for this problem earlier, we said pi over 6 plus 2k pi. And we said 5 pi over 6 plus 2k pi. So you would do those steps. You know, if we hadn't done this problem, you would do those steps here. For cosine of theta equals 0, draw a little unit circle if you want to, but you're going to find pi over 2 and 3 pi over 2 as two of the answers. And then you also need to add 2k pi to each of these. So all solutions looks like we have 4 families of solutions. So pi over 2 plus 2k pi, 3 pi over 2 plus 2k pi, pi over 6 plus 2k pi, 5 pi over 6 plus 2k pi, where k is any integer. K is any integer. There's another way that we could write this, actually. I think I'm going to put a box around this and say that this is okay the way we wrote it. But I do see a simplifying step we could do. For this one, I'm going to say either one is okay. Because this simplifying step, I don't know, it seems less obvious than some of the other simplifying we've done. So I notice that pi over 2 and 3 pi over 2, these solutions that we wrote, they can be merged, right? Because they're pi apart from each other. So you could say theta equals pi over 2 plus k pi. And then you still need to list pi over 6 plus 2k pi and 5 pi over 6 plus 2k pi. So either one of these is good for me. If you want to think of this as 4 families of solutions, or if you want to think of it as 3 families of solutions. Let's do a little bit more. Let's move this away. Let's see. So I feel like so many of the problems that we've been doing have been sine and cosine. And then you might say, what about the other ones? So let me say, remember, sine, cosine, cosecant, and secant have period 2 pi. So I'm going to say, because of that, solutions usually have plus 2k pi. And that's what we've been doing in most of our answers. The reason why I'm saying the word usually is because there are those cases where sometimes we can merge 2 solution sets, like 2 families of solutions get merged into one, and then it becomes like k pi. But in general, you find in these problems, we've been finding usually 2 families of solutions with a plus 2k pi on the end of each of them. What if we had a problem with tangent or cotangent? Well, they have period pi. So if you have a problem with those, solutions usually have plus k pi without the 2. So I'll show you one of these. I'll do this one, and then I'll have something else for you to do after this. Let's say we want to solve cotangent of theta plus 1 equals 0. Cotangent. All right. I think that the first thing I would do is probably rewrite it in the basic form. Subtract 1 from both sides. Cotangent of theta equals -1. Basic form. All right, now, do we know anywhere where cotangent of theta equals -1? Honestly, we might not know off the top of our head, so let's do a little bit of work. I know that cotangent can be thought of as cosine of theta equals cosine of theta over sine theta, so we could think of it this way. That might help. Because in fact, we're trying to solve this equation. We can do like things that we would do in algebra. We can multiply both sides by something, divide both sides by something. What if we multiply both sides by sine of theta? We get this. This is still equivalent to the original problem. Do we know where this happens? When I say where, I mean like for what value of theta? Do we know a single value of theta where this happens, maybe? Well, I think the answer is let's do a unit circle. Scratch work unit circle. And let's say on the unit circle, cosine would be the x-coordinate, sine would be the y-coordinate. So I need to think of a place where the x-coordinate and the y-coordinate are almost the same, except one of them has a minus sign in front. So they're like the same number, but one of them has a minus in front. The sign has a minus in front. Yeah, how about this point? This point comes to mind. What is this point? This is negative square root of 2 over 2, comma, square root of 2 over 2. Doesn't that satisfy this? So I came up with that because I was trying to think of a place where I would get the same coordinate, except the cosine one is the negative of the sine one. So they're the same number, except there's a minus in front of this one. So I'm going to say this happens when theta equals 3 pi over 4. That's the angle that I drew there. If you're not totally convinced by the picture, you could also check. You could say, you know, sine of 3 pi over 4 equals square root of 2 over 2. Cosine of 3 pi over 4. This little part I'm doing here, I think, is optional, but you could check that and then be like, all right, so when I put one on top of the other, I do get negative 1. So we're going to write all solutions. And I'm going to say, remember, cotangent has period pi. So for that reason, the solution set is going to be the answer we found plus just k pi. Don't say 2k pi, just k pi. If you were to draw a graph of cotangent, which we did a while back in an earlier section, if you were to draw a graph of cotangent, you would see that it repeats itself every pi units. So if there's an answer at 3 pi over 4, there's also going to be an answer exactly pi later. You could kind of tell from the unit circle too. If you add pi, you wind up here, and you could check that that is also a solution. All right, so the point of this problem was mostly to show you one that used tangent or cotangent because they have period pi, and also tangent or cotangent, I would probably try to rearrange them into terms of sine and cosine and work with it from there. All right, let's do one more problem. I'll give you one more. I'm going to give you one to do, and we'll use this to wrap things up. I'm going to ask you to solve cosecant squared theta minus 4 equals 0. And I'd like you to pause and give that a try, and then check back with me. All right, so this one's a little bit tricky. But there's two different ways that I can think of that we could approach this. One of them is we could add 4 to both sides. And then take the square root of both sides. We have to do something about that squared, right? So take the square root of 4, you get plus or minus 2. Cosecant. It's 1 over sine. And it's equal to plus or minus 2. So, does this ever happen? Yeah, this could happen, because this means sine of theta equals plus or minus 1/2. So really what we've done is we've kind of turned this into two problems, right? Sine of theta equals 1/2, sine of theta equals negative 1/2. And those are two basic trig equations. And they almost feel like things that we've done today. Did we do one of those? Did we do sine of theta equals 1/2? No, we didn't. We did sine of theta equals 0. So we didn't, I don't think we did sine of theta equals 1/2. Anyway, you could work with it from here. I'm going to show you there's another way that we could have started this problem also. But anyway, unit circle, where does sine of theta equal 1/2 or negative 1/2? So these are the places where it equals 1/2. And I think I know what those angles are. And then there are two places where sine of theta equals negative 1/2. And I think I know what those angles are. So these four solutions are pi over 6, right? That's the first one, pi over 6. That's the next one, 5 pi over 6. The next one is 7 pi over 6. And what's this last one? This last one is when you go almost all the way around the unit circle. We've gone 11 pi over 6. And all solutions, we're going to try to fit this on the rest of this page. All solutions could be written as these things plus 2k pi. And it does look like you could merge some of these together. I think in a previous problem I said that that was optional, so I'm not going to do it here because I'm out of space. There's one more thing I want to show you about this problem, though. Okay, where k is any integer. All right, so we did it. We found these 4 solutions, and then we added 2k pi to all of them because it's cosecant, and cosecant does have a period of 2 pi. I said there was another way that we could have started this problem, so I want to show you, some of you might have thought of it this way. So what if you factored it? You factor cosecant squared theta minus 4 equals 0. I'm going to zoom in on this. To cosecant theta minus 2, cosecant theta plus 2. This is another way to approach the problem. And then it looks like you have 2 problems to solve. But what I want to show you is that this leads you to the same steps. It leads you to here. It means cosecant of theta either equals 2 or cosecant of theta equals negative 2. So either way, I think, is the same amount of work. So it's just a matter of which way did you prefer to think of it. Were you adding 4 to both sides and then taking the square root of both sides? Or were you factoring? They both lead you to this place. Now, I think I said that was going to be the last problem, but I guess I lied because I thought of something while we were doing this, so I want to do one more. All right, note. The problems we've done. So far in this lesson have asked us to solve the equation. This means find all solutions. Just give you a chance to see that. We've used plus 2k pi or plus k pi to make sure we are providing all solutions. Okay, so that's correct. That's what we were supposed to do. However, there could also be problems that ask, given a trig equation, find all solutions in the interval 0 to 2 pi. I'm going to put this in quotation marks. Like, you could get a problem of this type. I guess I have to move away the other page now. In this case, we don't add plus 2k pi. So, I'll show you an example. Let's do one. Given sine of theta equals negative square root of 2 over 2, find all solutions in this interval. We'll do this together. It seems like it's going to be the same thing we've done, except we're not going to add 2k pi. Why do you think it's asking about this interval? Like, why square bracket 0 to 2 pi? Well, it's because this means it's kind of on the first pass around the unit circle, right? Like, what values of theta would be found on the first loop around the unit circle? We could start at 0, and if you went all the way to 2 pi, you'd be repeating that point that you already started at. You'd be coterminal with that point. So sometimes a problem will ask you just for solutions in this interval. They basically want just the things in the first loop or the first iteration around the unit circle. All right, so do we know anywhere on the unit circle where this happens? Yeah, this is the y-coordinate of a terminal point. I know two places that have a y-coordinate of negative square root of 2 over 2, and it's these two places. So I'm going to say from the unit circle, Solutions in the interval 0 to 2 pi are theta equals, what's this first one? We went in the positive direction, and we go a little bit past pi. We go 5 pi over 4. And what's the other one? Go around in the positive direction, 7 pi over 4. And that would be it. That would be the answers. Don't add 2k pi to it for a problem that's phrased this way. All right, so I'm going to say don't add 2k pi. And also double check that your answers are in the correct interval. 5 pi over 4, is that between 0 and 2 pi? Yes. 7 pi over 4, is that between 0 and 2 pi? Yes. So we're fine. This is good. That's the correct answer. The reason that I'm encouraging you to double check that your answers are in this interval is because, you know, there are other ways to get to these points. Like, what if you went in the negative direction? What if you said negative pi over 4? Is that okay for this problem? Like, theta equals negative pi over 4. That gets you to this point. That would be a wrong answer because negative pi over 4 is not in the given interval. So technically, it would satisfy this equation, but it would not satisfy this condition. So these are the only two correct answers for this. For the same reason, that's why you can't add 2 pi to this. You wouldn't be in this interval anymore. All right, so I think we're going to wrap things up here. All right, so we've done a lot of practice problems. We've done a lot of different types of problems in this section because the last couple of problems that we did were ones that I had in my notes as kind of optional problems if we had enough time, and I decided to go ahead and do them anyway. So you got to see some that have cotangent and cosecant and things like that. So there's still, the next lesson is still going to be about trig equations. So make sure you understand this lesson before you watch that one, because in that one, the problems are going to get harder. These were basic trig equations, and there's going to be some other ones that we have to address also. All right, so that's it, and I'll see you soon for that next one. Take care.